Okay, might as well get started here. All right, so if we take a look at the lesson sheet, so I'm going to have you start on a couple of these because we've seen this before. So we talked about this idea of using basis vectors to write any other vectors in, we talked about 2D, how we could use the vector I hat or J hat, which is just the vector 1, 0 and 0, 1. Well, presumably we can do something similar in 3D. So we've got the vectors I hat, which now doesn't represent 1, 0, but 1, 0, 0, J hat, 0, 1, 0, and K hat, 0, 0, 1. So what I want you to do is just draw a couple of quick diagrams to represent these two vectors in 2D. So this would be on a Cartesian plane, and then these three vectors in 3D, so on a 3D Cartesian space. All right, and then what I want you to do is write these vectors. Now again, how do I know this represents a vector? Well, because I'm telling you, it's the vector 5, -2 as opposed to the point 5, -2, and this is the vector 6, 3, 4. Okay, so I want you to write these two vectors as linear combinations of these standard basis vectors. And just to recall what a linear combination means, it means that I'm allowed to add and subtract expressions, okay, and take scalar multiples of those expressions. So 2x plus 3y is what we call a linear combination of the expressions x and y. And we can take linear combinations of objects like vectors. Okay, so take a couple of minutes to answer question 1. Okay, so we're back. Let's take a look here at these. All right, so if we take a look here, so we know that on the Cartesian plane, I and j just represent the vectors 1, 0 and 0, 1. And then in 3D, well, you just have something very similar. Here you've got the vector of magnitude 1 going in the x direction, so that would be 1, 0, 0. The vector j, sorry, going in the y direction, 0, 1, 0, and the vector k in the z direction, 0, 0, 1. Okay, so all this gives us is an alternate way to write these vectors. In other words, as a sum or difference of these, what we can call component vectors. Okay, and I'll say something about that in a second. All right, so here, if I want to write 5, -2, okay, well, I can just write it as 5 times the vector 1, 0 minus 2 times the vector 0, 1. Now we can justify that by using our properties of vectors. Okay, so what you can do is use scalar multiplication and subtraction. All right, because here you've got 5 times 1 and 5 times 0, so this would give you the vector 5, 0 minus the vector 0, 2. And then if you subtract those two vectors, you get the vector 5, -2. Okay, but very often, instead of writing it in this notation here, is we use our representatives for vectors 0, 1 and 1, 0. So an alternate way of writing vector 5, -2 is to write it as 5i minus 2j. Okay, now we just talked about the vector properties in 2D, but as we're going to see in the next question, is these properties in 2D extend to 3D. Okay, so you can write vector 6, 3, 4 as vector 6i plus 3j plus 4k. But essentially, you're applying the same rules to 3-dimensional vectors as you did to 2-dimensional vectors. So first, you would use the distributive property. So the x component here would be 6. Then when you add these vectors, you're going to be adding all the x components. So 6 plus, well, 3 times 0, 0, 4 times 0, 0. So you just get 6. And then similarly for the y and z components. All right. Now, some of you, in fact, somebody had brought up this idea. This sounds a lot like the idea of components when you're dealing with, say, force vectors in physics, and that's exactly it. But what you do in physics is you take your vector, say, you take, say, a vector, 20 newtons east, 30 degrees south, and then you'll write that as the sum of an x component of the force and a y component of the force. In other words, a horizontal component and a vertical component. Okay? But you have to calculate these. This kind of goes the other way around, is the vector is given as an x component and a y component. And then if you want to know a direction or you want to know a magnitude, you have to calculate it. Okay? Now, we talked about going in this direction becomes much more complicated when you're working in 3D. So what we do instead is we define a vector, or as an example of force, as given the x component, given the y component, and given the z component, and the sum of these three gives you your 3D vector. Okay? So again, the advantage of this definition of a vector, by giving it as a sum of these three mutually perpendicular components, is that the algebra of adding, subtracting, scalar multiplying these vectors is much easier than using the explicit method of giving a magnitude and describing the direction. Okay? So while we lose the fact that when I look at this here, it's not immediately clear to me what the magnitude is. I can't just look at this and give you a number. I have to do some calculation to determine the magnitude. But what we get in return is much easier algebra. Okay, and we'll see how that works in a second. All right, so any questions on how we can use these standard basis vectors to represent vectors in either 2D or 3D? No? Okay, so let's move on to the next question here. Now, if we were in class, I would be able to show you a nice 3D model. I'd use a nice big Cartesian 3 space to justify the idea of scalar multiplication or addition or subtraction in 3D. Okay, so you'll have to imagine it. What you can do is, on the side of your table, if you want, on the side of your table, think of a x-axis, y-axis, and put like some, put a broomstick perhaps going upwards, and you can create vectors and add them together and see how scalar multiplication and how vector addition would work. Okay, that's what I would have done if we were in class. So what I would like you to do, though, oops, that's not what I'm going to show you. I want you to write rules that you think would be reasonable. And again, you can try to think of a 3D model, think of a corner of a table and see if you can make sense of these rules for taking the opposite of a vector defined in 3D, scalar multiplication of a vector, and the addition or subtraction. Okay? And now what I want you to try to do is I want you to try to use this new definition of vectors to prove one of the properties, okay? Because we're going to see how having this definition of vectors is also going to make proving our properties much, much easier. Okay, so I'll give you a bit of time, see how far you can get with this, but I'll show you what I would expect if I was asking you to prove one of these properties. All right, so I'll give you maybe 2-3 minutes to work on numbers 2 and 3, and then we'll come back and look at them together. Okay, so we're back. So let's take a look at how we are going to define these operations now on 3D vectors. Okay, so if we start with the opposite and scalar multiplication. Now, when you think about it, finding the opposite of a vector is just a special case of scalar multiplication, and we define it in the exact same way as we defined it in 2D. Okay, so if I have a vector x1, y1, z1, the opposite of that vector, okay, is just given by negative x1, negative y1, negative z1. Okay, so again, this is not too surprising if we kind of look at our 3D space, that if I have some vector defined here, so think about the x component, the y component, and the z component, if I just take that vector and flip it the other way around, we see that the only thing that will change is now the x component, if say it was positive in that direction, will now be negative in the other direction. Okay, so all it's going to do is going to take the opposite of each component of your vector. Okay, and in general, scalar multiplication is just about multiplying the individual components by the scalar multiple, exactly like what we did in 2D. And similarly, when we're adding and subtracting vectors in 3D, we see that it's just a matter of adding and subtracting the individual components. So what's great, and this is the brilliant idea behind algebraic vectors, is that you realize that operating on vectors comes down to just operating on real numbers, because all you're really doing is doing operations on the individual components. You're either multiplying the individual components by a number, or you're adding and subtracting the individual components. Okay, so we've reduced doing doing operations on these vector objects to doing operations on real numbers. And we know a lot of things about how to operate on real numbers. Okay, so as an example, let's see how we could use this to prove our distributive property. Now, back when we were talking about geometric vectors in the previous sections, okay, we gave a pictorial justification for this this property. Okay, that if I multiply the sum of two vectors by some scalar, that's equivalent to multiplying the individual vectors by that scalar and then adding them. So our good old distributive property. So let's see how we could do this. So if we want to prove this, I'm going to do what I usually do. I'm going to start with one side and hopefully show that it's equivalent to the other side. Okay, so I start with the left side of my equation. So I'm just writing it out now. So I'm just going to use the same vectors that I defined in the previous question, u and v. Okay, and I've just written u and v out as their ordered triple representations. Okay, so now what I'm going to do is I'm going to apply my addition rule, because inside this bracket now I have the sum of two vectors, and I've defined what it means to add two vectors. So I just add these two vectors, so x1 plus x2, y1 plus y2, z1 plus z2, and my justification is that this is my addition rule. Then I'm going to apply my distributive property, which says that if I am multiplying a vector, because now this represents a single vector, by a scalar, okay, I just multiply each component by that scalar. So now all I do is I just take this k and I multiply it to each component of the vector. Okay, and this is where now I can make use of what I know about real numbers. And I know that real numbers follow the distributive property. So now I'm no longer working with vectors. I'm just going to work with this individual component. And in this individual component, k is a real number, x1 and x2 are just real numbers, hence they're distributive. So I can apply my distributive property for real numbers. Okay. Okay, so this is by the distributivity of the real number system, because I'm working component by component. Okay, and now that I've applied the distributivity of the real number system, I can now start to go backwards. I can now write this as the sum of two vectors. So I use my addition property backwards to now write this as two vectors. Okay, you see that if I add these two, I get what I had previously. And now I'm going to apply my distributive property backwards to rewrite that expression in this way here. And look what we've just shown, k times u plus k times v. So I have now proven that vectors are distributive under addition and scalar multiplication. And what was the trick here was using the fact that I know that real numbers are distributive. Okay, so this is why we call these algebraic vectors, because operating on these vectors comes down to just operating on real numbers, because in the end, I end up operating on the individual components. All right, so is there any question on what we've seen here? Okay, so we've seen that operations on vectors are now defined by working with the individual components as opposed to working with angles and triangles and trigonometry. Okay, so we notice here that to do all of this, you don't ever need to know what the magnitude of the vector is, and you don't need to know a specific direction. Everything is done by working with the individual components. All right, any questions there? All right, so what we have now is we have all the basic components to do algebra with vectors. Okay, we have a system for doing for adding, subtracting, multiplying vectors geometrically, meaning using trigonometry. Okay, when the vectors are given explicitly as a magnitude with a direction. And now we have a way of operating with vectors in this algebraic sense, where vectors are given as ordered pairs, but now also ordered triples, meaning we can do these operations in 3D. Okay, so we have all the basics. So before we move on to the next big topic, which is, what operation have we not yet done with respect to vectors? Can anybody think of, and I've referenced this before, what's one operation we really haven't come across yet? Division. So what do you mean by division? Be more precise, because I can, we've, I can say that if I have a vector u, I can divide that by 2, because that's the same as 1/2 times vector u, so scalar multiplication. So in some ways we have brought in this idea of division. But I see something interesting. So the last person was a little more precise, is what does it mean to multiply two vectors? In fact, is there a meaning to multiplying two vectors? So this is what we're going to start to explore now as we go into the next section. All right. But before we do that, I want to talk a little more about this idea of basis vectors. All right. So, and I'm going to focus my attention on 2D vectors for now. So we already know that I can take these vectors I and j, and I can write any vector as some linear combination of I and j. So this is, say -3i plus 4j. And I can write any vector on the Cartesian plane as a combination, as a linear combination of these two vectors. All right. But I notice we called these the standard basis vectors. So the question is, do my standard basis vectors have to be the only possible ones? Could I use other vectors? Could I use these two vectors to define any other vector on the Cartesian plane? Well, let's pick some random vectors. So let's say I call this P and I call this Q. Can I write this vector as some linear combination of P and Q? What do you think? What do you think? Is this possible? Probably. That's hedging your bets. Well, before I do that, I want you to think about how I might do this. Okay? So remember what a linear combination does. It allows you to multiply vectors by some scalar, and then add them together. Okay, and obviously if your scalar is negative, it might involve subtraction. But remember, how does one add vectors when they're tail to tail? What represents the sum of vectors when they're tail to tail? The diagonal of the parallelogram. So imagine if I tried to form a parallelogram, let me put these out here, and let's say something. Hey, I realize, wait a minute. It looks like if I multiply P by about, I don't know, 2.5 perhaps, and here maybe I multiply Q by, 1.2 Q, do you see that if I take 2.5 times P plus 1.2 times Q, look what I get, this vector here. And you start to realize that you should be able to do this with any vector. Maybe this here is like, 1.25 times P plus 2.6 times Q. And any vector on the Cartesian plane, you realize you should be able to write as a linear combination of these two vectors. So that means you can have lots of basis vectors. Now, the question might be, well, why in the world would I want to use these two as basis vectors if I can use these really easy ones? And that would be a very good question. And unfortunately, I'm going to have to say that I'm going to reserve the answer for a little later on. We are going to see that there will be scenarios where it might not necessarily be preferable to use two unit vectors that are perpendicular to each other. So for now, we're just going to explore this possibility, and later on, we're going to see how it might be useful to use other vectors other than these two perpendicular unit vectors. Okay, so real quickly, I want you to, and I'm looking at the time, so we're not going to spend, I'm going to give you too much time to look at that, but I want you to see what can you do to write the vector 11, negative 5 as a linear combination of 2, 3, and 4, 1. So what I don't want you to do is to draw me a picture, okay? But what I do want you to do is to set up an algebraic way to figure out how you could write 11, negative 5 as a linear combination of 2, 3, and 4, 1, okay? And if you have time to get to B, think about B, okay? But I want you to, at the very least, set up part A and see if you can actually solve. All right, so let's come back. So normally I would have given you a little more time, but I'm cognizant of the time. I'm already going over a little bit. Okay, so let's take a look at how we could do this. All right, so I want to write 11, negative 5 as a linear combination of these two vectors. So what does that mean? It means that I'm allowed to multiply the vectors by some constant and then add them together. So essentially what I'm looking for is what are these two constants that I'm going to multiply to each of the vectors, okay? And it's not necessarily the same constant as we saw in our diagram earlier. So all I do here is now I apply my properties. So I'm going to multiply A to both of these two components, B to those two components, and then add the individual components. So I end up with this here, okay? That, in fact, I can go further, add them together. But now I realize that in order for these two vectors to be equal, I need the x components to be the same and the y components to be the same. And so lo and behold, what we've done is we've created a system of equations, okay? So determining these values is all about solving this system of equations, all right? So I go ahead and solve this system of equations, and, not the nicest numbers in the world, but again, still fairly easy to solve. So that means that this vector 11, negative 5 can be written as negative 31 tenths times the first vector plus 43/10 times the second vector. And you can imagine that you could go through this process for any vector in R2. Okay, so any vector can be written as a linear combination of those two vectors. So then the question becomes, well, can I use any two vectors as as basis vectors for R2? Okay, and then of course one could think about R3. Can I use any three vectors in R3 to as basis vectors? Okay, although we're just going to stick with R2 right now. And if you think about it, okay, so we saw how, similar to before, we have these two vectors, and by taking, multiple of the first plus a multiple of the second, you can get to this other vector. But there are some conditions, okay? Can anybody think of one vector that you definitely don't want to use? You think of one vector that just isn't going to be too useful if I'm trying to, yeah, there you go, the good old zero vector, okay? Because imagine if I take a linear combination of, say, I don't know, I just pick 2, 3 at random, okay, plus some multiple of 0, 0. Well, what do I end up with? I just end up with A times 2, 3, meaning I just end up with vectors that are parallel to 2, 3, okay? So think about what vectors are parallel to 2, 3. Well, it would be, this vector and this vector and this vector. Or if the multiple is negative, and you realize that all you're getting are vectors in this one direction. That definitely, there's no way I could generate that vector using just 2, 3. Okay, and then I see another good suggestion is the vectors cannot be parallel. Okay, now I kind of give a justification here, but let's kind of, give a visual justification. If vector P and vector Q are parallel, even if Q was going in the other direction, well, what happens when I just add two vectors that are in the same direction? I just get more vectors that are in that same direction. So it causes a similar problem to number 1. Is there's no way I could describe that vector using vectors P and Q. Okay, and I give an example here. 1, 2, and 3, 6 are parallel to each other. That when I simplify this, I can just always write it as some multiple, because A and B are just numbers, of the vector 1, 2. Okay, so what this tells us is that any vectors can act as basis vectors as long as they're non-zero and the two vectors are not parallel. So if we just do a very quick scan of the notes here, okay, we've got our standard basis vectors in 1D and in 2D. In 2D and 3D, ij and k. Okay, our operations on 2D vectors and 3D vectors work in the exact same way. You're operating solely with the components of the individual vectors. Notice here how I can use my ordered pair or ordered triple notation, or I could also work with my standard basis notation. Okay, the book really likes this notation. I'm a bigger fan of that notation because it's less writing. Okay, and then here we have that any vectors in R2 any two vectors can be used as basis vectors as long as neither of them are 0 and the two vectors are not parallel. Okay, and if basis vectors, if you have two valid basis vectors, what we say is that they span R2. Okay, meaning that you can use these two vectors, okay, to write any other vector in R2. So that's just the word we use. We say it spans R2. Okay. The only other thing here is, again, just an upgrade from 2D, is this idea of finding the vector that joins 2 points. It works in 2D the same way that it works, in 3D as it works in 2D. Okay, we saw in 2D that to find the vector that joins 2 points, we just have to subtract the second minus the first. All right, so that's it for this lesson here. So yep.
Just a quick question.
Yep.
What if, like, r squared assumes all positive numbers, right?
No. Remember what this just represents. This is another way of writing the Cartesian plane. R2 just represents all vectors on the Cartesian plane. So it's not a square. It's just a symbol representing. So this would represent what we call 2 space. And R3, we saw earlier, just represents 3D space. Okay? It's just a symbol.
Thank you.
Yep. Anything else we want to ask before we go?